If you've ever looked up at the night sky and marveled at the twinkling stars, it's hard not to wonder, are we alone? And if not, why? It seems as though the universe was created just for us. The more scientists learn about the cosmos, the more they realize that life as we know it depends on a delicate balance of physical constants. If these constants were even slightly different, life as we know it couldn't exist. For example, if the gravitational constant were even a tiny bit bigger or smaller, stars like our sun wouldn't form or they would burn out too quickly for life to evolve. Or if the strong nuclear force were slightly weaker, hydrogen atoms wouldn't form and there wouldn't be enough of the heavier elements for life to get started in the first place. Many scientists have come to the conclusion that the universe was finely tuned for life. But why? In this video, I'm going to look at one scientist's answer to this question, an answer that has both intrigued and frustrated scientists since it was proposed over 40 years ago. I'm also going to show you how you can use this idea to make your own stunning images of the cosmos like the one you see here. This video comes with a quiz that lets you check how much you remember. Imagine you're playing a game of cosmic darts. The target is the center of the Milky Way galaxy and you're trying to hit the solar system, but it's really hard because the solar system is very small compared to the galaxy as a whole. In fact, the distance between the center of the Milky Way and the Sun is roughly 30,000 times bigger than the distance between the Earth and the Sun. To get to the solar system, your dart has to fly through a cloud of gas and dust. You think that there would be lots of collisions and your dart would probably hit something long before reaching the solar system. But your dart doesn't interact with the particles in the gas cloud at all because it's made of antimatter. When the two touch, they annihilate each other. And since you're playing this game in the early universe, there's plenty of antimatter around. You might think it's pure coincidence that you managed to navigate the cloud without colliding with anything, but what if you didn't have to? What if the game was rigged? Maybe the entire early universe consisted only of equal amounts of matter and antimatter, but then over time, some of the antimatter mysteriously disappeared. That would leave behind a lot of regular matter that could then form stars, planets, and eventually us. When physicists first realized that the early universe may have contained a lot of antimatter, they thought it would solve the problem of why the universe seems to be finely tuned for life because according to the best theories there should have been equal amounts of matter and antimatter in the early universe. But if that was the case, they reasoned that all of the matter and antimatter would have annihilated each other, leaving nothing but light and we wouldn't be here to wonder about it. But instead, we find ourselves in a universe full of stars and galaxies and planets and life. So the idea that the early universe consisted of mostly matter and antimatter got some traction among scientists. It didn't explain how the antimatter disappeared, but that wasn't really important. For many scientists, it was good enough to simply point out that the matter-antimatter asymmetry was an example of a so-called anthropic coincidence. We just happen to live in a universe where the amount of antimatter happened to be just right for life to evolve. But then in 1978, one scientist came up with a different idea. He suggested that the reason we find ourselves in a finely tuned universe is that life itself creates the conditions for its own existence. Let me explain. According to quantum mechanics, empty space isn't really empty. It's full of virtual particles that pop in and out of existence all the time. Some of those virtual particles are pairs of matter and antimatter. And normally they'd annihilate each other right away, but under certain circumstances, they don't. They can get trapped and remain visible, becoming real particles. And here's the kicker. If the particles aren't trapped, their distribution is random. There will sometimes be more matter particles and sometimes more antimatter particles, but overall there will be equal amounts of both. However, if the particles can get trapped, then the distribution can change. There can still be equal amounts of matter and antimatter in total, but now there can be more matter particles in some places and more antimatter particles in others. Now imagine you have a big box filled with these particles and let some of them interact with each other. If there are regions with more matter and regions with more antimatter, then some of the particles will annihilate each other wherever they meet, but that won't happen everywhere at the same time. In some places, the matter and antimatter will continue to accumulate, but in other places, new matter-antimatter pairs will pop into existence and the number of particles will stay roughly the same. In 1978, the physicist Andrei Sakharov pointed out that this process can create a kind of feedback loop. Regions with a surplus of matter or antimatter will continue to produce more of that type until the entire universe reaches a state of maximum entropy in which all matter-antimatter pairs have annihilated and there's nothing left but a smooth distribution of regular matter. But the crucial point is that if there are fluctuations in the particle distribution, then it doesn't matter whether they're caused by quantum effects or by feedback from later times. In either case, the result is the same, a non-random distribution of matter. In the regions where matter dominates, stars can form and life can evolve. So according to Sakharov's idea, it's not a coincidence that the conditions of the universe seem to be perfectly suited for life. Instead, life creates the conditions for its own existence. A great example of how physics and biology intersect. Sakharov's idea was initially quite popular, but over time, it's gotten less traction. One of the reasons is that it's just difficult to understand exactly how the particles would have to interact to cause the particle distribution to shift in the first place. Another issue is that it's not clear how this process would affect larger scales. After all, the universe is much bigger than a box full of particles. But recently, researchers found a way to make sense of the mechanism by using ideas from condensed matter physics. In their model, the particles correspond to so-called spins, which are quantum objects that can be in two states. In their case, the spins represent the particles of the early universe. Like particles, they have a certain interaction that determines how they behave. And depending on the strength of the interaction, they can exhibit different phases of matter. At weak coupling, their behavior is chaotic and there are no long-range correlations between the spins. At strong coupling, they form a so-called condensate in which all spins align with each other. But most interestingly, in an intermediate phase, they self-organize into a kind of checkerboard pattern called a supersolid. This is the state that the researchers say resembles the early universe with a surplus of matter in some places and antimatter in others. This checkerboard state arises because of quantum effects, but it persists even when quantum effects become unimportant. So in a sense, it's a kind of quasi-particle that behaves like a particle. And it's this quasi-particle that would have created the conditions for life, according to their scenario. To me, this is such an exciting idea because it makes the emergence of life into a question of whether the conditions are right for life. And whether the conditions are right for life is a question that you can actually address with math and simulations. And this is how you can make your own beautiful pictures of the early universe and maybe find out whether Sakharov's idea is correct. The simulation code is available online and the project comes with a guide that explains how to use it. The visuals are generated with a custom transfer function that I wrote myself and which is included in the project. After running the simulation, you can change the parameters and see how it changes the appearance of the universe. Whether or not Sakharov's idea turns out to be correct, I think it's safe to say that we live in a finely tuned universe. On the smallest scales, the strong nuclear force brings protons and neutrons together to form the nuclei of atoms. Without this force, atoms wouldn't exist and neither would we. On the largest scales, gravity keeps the atoms together in stars and planets. Without gravity, stars wouldn't form and again, we wouldn't be here. It seems as though the laws of nature and the values of the physical constants are just right for life. But there's another aspect that we haven't talked about yet, and that's the ultimate origin of the constants themselves. Where do they come from? I talk about one possible answer in this video. It's a mind-blowing idea that connects the arrow of time with black holes. Thanks for watching. See you tomorrow.